Hey friends, welcome to Ghosh for AI. My name is Sharnendu Ghosh and today I'm very happy to bring you this video. So I have decided to make a few videos on some easy to implement machine learning algorithms. I have seen that many people who have just started their research career are diving straight into very complicated algorithms like convolutional neural networks or say recurrent neural networks or deep learning and these kind of stuffs. But I believe that it is very essential to understand some of the core concepts of artificial intelligence or machine learning. And for that, there are two approaches. One of it is the theoretical approach, in which one has to study some of the books or papers that clarify the basic concepts. And the other part is to develop your own machine learning algorithms, sometimes from scratch, sometimes by using some APIs. But the point is to get your hands dirty with coding. The more you code, the more you'll understand the internal dynamics or the what kind of computation is going on behind all these machine learning algorithms and why do these actually work. So I've also made another video in which I have described in more details or explained in more details that why one should not dive straight away into things like deep learning and why these basic concepts are necessary. If you have not seen that, I would say please you can check the link I've given in the description below. And other than that, I believe that these videos that I'm going to publish in the future, it will be helpful for newcomers. Now this video at present, it's basically about data processing. Now when somebody is working with machine learning, the first and foremost thing that one has to do is to process raw data. And to tell you that how one should do that, I have made this little video in which I will be trying to explain how a very popular dataset called the MNIST dataset is organized and how you can extract the information and how you can represent it in a very easy to use data structure. But before all that, I would like to ask you to please subscribe to my channel if you want to follow this and get updates for the new videos that I will be posting in the future. And also don't forget to click the bell icon for the notifications. Anyways, so as I was telling, in this video I will be talking about one specific dataset called the MNIST dataset. Now MNIST dataset, it is composed of around say 70,000 images which are basically of some handwritten digits. The digits were mainly taken from postal cards, and it's very useful for like image classification algorithms, like a typical image classification algorithms. Now it was somewhere proposed somewhere around say 1998 when Jan LeCun published his first paper on the first convolutional neural network. It was first disclosed around that time, and since then it has become one of the benchmark datasets to build algorithms on. Like whenever you are trying to build new algorithms, it is very common practice to work with some very simple dataset at first, and MNIST is one of those simple datasets in which you can build your own algorithms. Now for that, let me take you to the website of MNIST directly. So here, so this is the website of the MNIST database. Even if you do a basic Google search, MNIST database, it normally comes up in the first. Yeah, this is the second link. This is the main website, which is this one. So in this website you will be getting some downloadable links which will give you the train images, the training labels, and this is the test set, the test images, and the testing labels. So I will be explaining a bit more about what these labels are. But before that, I will just point you to the downloadable links, and also you can see the performance of various algorithms on these datasets and like what is the error rate on the given test set that they have provided. So right now I think the best error rate is somewhere around this 0.23. that is like a 99 point say about 99.7 99.77% accuracy, and that's quite a lot. That's like almost perfect, like, yeah, almost perfect algorithm. And this is like a committee of 35 convolutional neural networks with elastic distortions. But these are much more complicated things, which is like beyond the scope for newcomers. At first, one should understand some of the basic things of about machine learning and data processing and all those things. So I will explain more about how these files, like as you can see, I have told like there are 60,000 examples in the training set and 10,000 examples in the test set, but they have provided only like 10 files. Sorry, they have only provided like 4 files, and all of these 60,000 images are encoded in a specific format within these files. And I will show you a code in which you can access all those information and also convert them to a favorable data structure. If you study the page more, you can learn a bit about the history of how the dataset was collected, and also if there are some information about how the files are formatted, and that will help you in extracting the pixel intensities, or like the images or the labels of the images. Okay, so again, I have used the term labels again and again. So basically the digits are from 0 to 9, and each of those 0 to 9, these are like labels for the images. So if you have, say, a specific image with say 3 written over it, so the label of that image is 3. So you have 10 labels 0 to 9, and each label corresponds to one of the images, or rather each of the images have a label corresponding to them. Now, okay, another thing that you might want to check out is the paper in which this was first proposed. This is called gradient based learning applied to document recognition. It was one of the first, it's not one of the, it is the first convolutional neural network ever proposed, and that makes it is one of the most important papers in the history of machine learning. So if you just go to this Google Scholar and let's check gradient based learning applied to document recognition, and you will see that this paper has almost like 13,000 citations, and that's quite a big 13,000 citations. You don't get that much amount of citations if your paper is not good. Okay, so this was one of the first convolutional neural networks that was ever proposed, and if you go down, you can also see the image that they have provided of the CNN. Wait a second. Yeah, so they have shown how they have proposed this convolutional neural network. It was called the LeNet 5 because it was a 5-layer network, but these are much more complicated things which I'll be discussing later. This is just for like fancy viewing right now. And if you scroll down, there is a lot of statistical tests that has been done on this MNIST data. So you can see okay, so these are the images. You see, these are like 28 cross 28 images, each corresponding to one of the 10 English digits, and these are handwritten samples. And as you can understand that handwritten samples obviously have much more variance as compared to like typed samples, and hence it is a much more difficult task. And for that we have this convolutional neural networks have proved to be quite efficient as compared to the previous algorithms that came before 1998. And so like that kind of started the deep learning era in computer vision. Okay, so now if you go through this paper, you can learn a bit more about it, but right now our focus is on the MNIST dataset. Now, as I said, these files they are basically encoded in a binary format, and if the binary data is traversed 1 byte at a time, then by setting some specific offsets, like taking a few amount of bytes at a time, we can extract some specific information. For example, in the training set, so out of these four images, out of these four files, one of them you can see is a train labels files, like it's the label for the training images. And if you check the offset corresponds to every byte in the coded binary string. So starting from 0, if we collect a 32-bit integer or a 4-byte integer, we will be getting a value called 2049, and that number is called a magic number, which tells you whether that this file is a label file or a image file. Next 32-bit integer, that's a 4-byte of integer, will give you a number called 60,000, which tells you how many samples there are in the file. And after that, every unsigned byte will give me a label. Now label values are given from 0 to 9. For the image files, it's a bit more complicated because images are 2D matrices which are of the size 28 cross 28. So to express that, so the first 32-bit integers gives us a number 2051, which corresponding to image files, and then the next 4 bytes or 32 bits give us the number of samples, that is 60,000, and the third set of 4 bytes and the fourth set of 4 bytes gives us the number of rows and number of columns. After that, every unsigned byte gives us a value of a pixel. Now the pixel values can be from 0 to 255, and 0 means background and 255 means foreground. The same format is followed for the test set label as well as the test set image file. Now this is a data structure that is not very programming friendly, we can say that. So in programming, we are normally habituated by using data structures like say arrays or lists or say dictionaries, things like these. But this is just a kind of a string of binary numbers. So we have to extract these values and organize them in a very feasible or suitable data structure. For that, I have written a code which you can find it in the GitHub repository, which corresponding to the name of this channel. Even in my future videos, I will be posting many codes, and I will always keep the copies in this repository that you can find in GitHub. And I would like you to follow these repositories in the future as well, to find new codes about new systems or new implementations. In this way, I think many newcomers or new researchers they will find a lot of help here. So sorry. So the name of the repository is the name of the channel, that is Ghosh for AI. And if you go down to users, you can find this repository. So I have only one repository at now because I've just started the channel basically. So we go into data processors, and here I have made MNIST loader.ipynb. So this is an IPython notebook file. Now IPython notebooks, it's basically an IDE for coding in Python, and it's a nice IDE in which you can do Python programming in a very structured way, and it is good for tutorials. It's very good for tutorials because you can have really nice formatted parts of text in between the lines of codes, and that makes it very easy to work with. So what we have to do is we have to clone this repository in our local directory, and then we can run it from there. So basically, if we click on clone here, and we will get a downloadable link, we copy it, and then we have to paste it somewhere. So let me go to my codes. So let us do this here. So we open a terminal in this location and say we clone the repository. So the link we copied, we can clone it by using this command git clone and then the link. It will take some time, and yes, now it's copied. So right. So we have the IPython notebook file in which I have written all the codes for loading the MNIST data. We can open a terminal again in this location, and we can open our notebook file Jupyter Notebook. So this is the command for opening a Jupyter Notebook IDE, and it opens IDE in the browser, and that is a very cool thing to have actually. So when we open the notebook, so as I told you that this is a very nice IDE in which you can have parts of your codes and also some nicely formatted texts to help you understand those codes. So it's very good for specifically very good for tutorials. So here we have a data loader for the MNIST database, and I've also given the links, or those 4 links which I showed you in the website also here, so you can directly download them from here, or I've also provided a little code in which can download the data for you. So I can explain the code, but it's mostly commented. If you follow the commands, it should be easy to understand the code. So here you have a directory in which you want to download the data. You have to keep this in mind because this directory will be needed for the other parts of the codes as well. So here I just create the directory which doesn't exist. We have the downloading URLs to download the data, and for all the URLs I basically call a function called URL retrieve, which will download the files for me. So if I run this part of code, I can use shift enter to run, and it will download all the images, rather not the images but the 4 files. Now I can check if the files have been downloaded properly or not. So the location was /data.MNIST dataset. So dot means I go to the previous folder, then I go to the previous folder again. So we have a folder called data, MNIST data, and we have these 4 archives. So these archives are, you can extract these archives manually using the graphical user interface, or you can also use this little code that I've written here, and that can be extracted very fast. So just let me run this code. Yeah, so this code will extract all the files from the archives, and also there is an optional code for removing the archives because we don't need them anymore. This part of code is basically for formatting the IPython notebook. It just puts the table on the left hand side. I did that so that it's it looks beautiful. Anyways, but it's not necessary. So I have provided the file descriptions here so that we can track how to traverse the binary sequence. So for labels, it's 4 byte of magic number, then 4 byte which says the number of samples, and after that every byte gives me a label. And for the images, we have 4 bytes of magic number, 4 bytes of which says the number of samples, then 4 bytes which says the number of rows, then number of columns, and then after that every byte gives me a intensity of a pixel. Now if you may be wondering that an image is like 28 cross 28, but we have like 1 pixel at a time, so how does that work? So basically what they've done is, so a 28 cross 28 image is basically 784 values which are organized in 2 dimensions. So if we read all those 28 cross 28, all the pixels in a 28 cross 28 image in a row measure format, like 1 row at a time, then we will see that we have 784 straight pixels that can be read, and they have basically written all the 784 pixel values from first to last for every sample. Okay, now what we'll do is we'll convert these ubyte files into something called Numpy arrays. Now Numpy is an API for in Python, and anybody who's like starting the machine learning journey, and especially if they are using Python, I would suggest that they learn a bit about Numpy. Though it's not a good thing to just go and learn APIs just from scratch, but these things should be learned more from on a necessity basis. But it's good to have some basic knowledge about Numpy. These APIs like Numpy, SciPy, and there are like things like Matplotlib. These are some basic APIs that you will be needing in your machine learning career. But you will learn them as you go. So I'll just show you the Numpy documentations just in case. So I think it's basically here, numpy manual, numpy basics. So if we go to here, like numpy basics, there are some, like what are the data types that are used in numpy, or how to create your array in numpy, and there are some many more things which you can study. So numpy, it basically gives you some tools to do some nice mathematical operations, which are very essential in machine learning. But again, like deviating from the topic. Okay, so basically we'll convert these ubyte files into numpy arrays for easy processing, and we will be creating a dictionary. Now in dictionary you can index the values of a dictionary by using a string. So in this dictionary there are 4 keys called train images, train labels, test images and test labels, and for each of those keys I will have a numpy array. So basically train images will return me a numpy array of shape 60,000 cross 28 cross 28. That means basically like there are 60,000 28 cross 28 images. Train labels will give me the corresponding levels of the images, and it's a simple linear array of length 60,000. The same for test images and test labels, when we have 10,000 image and 10,000 labels each. And now this code converts the ubyte files into a numpy array. So if you see, so for every file, every one of those 4 files, if the file ends with ubyte, because see the ubyte file ends with this string, if this ends with ubyte, I will be reading the file and then I will be extracting the information 1 byte at a time. So the first byte gives me the type, because it's like the magic number, if you remember. So it can be 2049 or say 20551. Pardon me, there is a mistake here. This should be 2051. 2049 is for labels and 2051 is for images. Just to confirm, if we go to the MNIST site, we can see yes, 2049 is for label files and 2051 is for image files. Even in the test set we can see 2049 is for the label files and 2051 is for the image files. So pardon my mistake in this documentation. I will fix this once at the end of this video. So in the code we store the type or the magic number in this variable called type, and then the next 4 bytes gives us the length of the dataset or the number of samples in the dataset. Now if the type is 2051, that means it belongs to training images. If the type is 2051, then it means images. So the category is basically images, and the next set of 4 bytes will give me the number of rows and number of columns. After that, every byte will give me a pixel value. Now if you see from the buffer, like I am treating the whatever I have read from the file as a buffer, and from that buffer I am reading one uint8 at a time, starting from an offset of 16. So if you see my number of columns, it ended in the ID of 16, like from 12, say 12, 13, 14, 15, those 4 bytes gave me the number of columns. Starting from the 16th byte, I will take 1 byte at a time, which will give me 1 pixel intensity of a specific location. So I will be extracting a uint8 format or a integer from the offset of 16 from the buffer, and I will store it in parsed in the variable called parsed. So parsed has basically become a numpy array in which all the pixel values are organized in form of a long chain. And if we reshape the parsed to get our required shape, that is of say 60,000 cross 28 cross 28, or say 10,000 cross 28 cross 28, depending on whether it's train or test, we will be reshaping it as length comma number of rows comma number of columns. If the type was 2049, then it is basically labels, and for that we will simply extract one integer at a time from the offset of 8, and each of them will give me a length, each of them will give me a label. And this line just makes sure that the shape of the array is exactly like, like this, like a linear array of 60,000 or linear array of 10,000. Now if the length is 10,000, then it's the test set. If the length is 60,000, then it's the train set. And now I will put this NumPy array that we have just created and in the dictionary. So in data dictionary, so if you see, the keys are organized in like this, like the first part is either train or test, that is the set, and the second part after underscore is images or labels, which is basically category. So category can be images or category can be labels. So given that, I generate the string set underscore category, and in that position I put the NumPy array that I have just generated. So after this loop is complete, we will have something called a data dict, in which we will have the all the information about the pixel intensities and the labels in a very nicely usable data structure. So let me run this. Okay, pardon me. Okay, so I'm supposed to, I think I changed this NumPy to like this. Okay, basically this has to be NumPy. Yeah, it should work. The problem was sometimes when I was making this code, I would have written a line like this, NumPy as NP, and maybe I made some changes probably here and I removed the line, but I forgot to change some other places where it was still NP. But anyways, this should work now. Yeah, so we have read all the 4 files, and now we have the data structure called data dict. We can check that, of course. Let me just insert a cell below and we'll just see. So data dict is a dictionary. So data dict dot keys. Let me check what are the keys of data dict. So data dict keys are test images, test labels, train images, and train labels. So each of these are represents a NumPy array. So let me show you, say test images. This should be a NumPy array. Now if I print the NumPy array, it's a huge array and it will like fill all of the screen. So let me just print the shape of the NumPy array for you. So yeah, so if you see, test images is giving me a NumPy array of 10,000 cross 28 cross 28. So if I want to show you one image at least, or rather the values corresponding to one image, it should be say 0, 0, comma. So I'm taking the 0th sample and keeping all the 28 cross 28 bits. So if you see, this is the array. So most of these values are 0, that is the background, and in some places we have values ranging from 0 to 255 that shows the parts of the text. So let me delete this cell for now. So okay, fine, we have this dictionary in which we can, from which we can be used in many machine learning algorithms in the future, but right now maybe if we want to save the images in a directory, for that of course, like these are values, and a human mind cannot perceive them as images until like it is shown as images to them. So to convert these values to images, we have a little code here in which for every set, that is train or test, I go through all the samples and I will read those images and I will save the images in a a directory which is specific of the class of the image. So all the images that represent 0 will be inside a folder called 0. All the images of 1 will be inside a folder called 1, like that. To do that, I will basically we have the Numpy arrays called images and labels, and if you notice that say for train images, it's for train image it's 60,000 cross 28 cross 28, and the labels are all 60,000. So for every 28 cross 28 image, I will have a label. So if you check this part of the code in more details, you will see that I have the data path in which where I'm going to save. After that, I will have something called the set. The set is either train or test, so there will be a folder which will be named either train or test. After slash, I will have something called a label. A label can be 0 to 9, so it will be a directory which will give me the name of the class. And finally followed by slash, and whenever I am saving the image, I will follow the same path structure, data path plus set, then plus labels, and after that I will represent each image by a 5-digit number, and I'll save it with an extension of .png using this function called imsave. Now imsave is a function which is given in another API called skimage.io. This is an API which is useful for many image processing algorithms, and it has a lot of image processing algorithms, and you can also see that in Google if you want. .io, oh pardon me, .io, skimage.io, say docs. Yeah, so if you see this documentation, you can see this skimage, the input output package under skimage. It has many functions like imread, imsave, imshow, and many other things. Even the root package of skimage or scikit-image has lots of functions corresponding to image processing. So so if you say like color, you see like there are a lot of functions which changes formats of colors and many other things. You can do a lot of image processing stuffs with this skimage API. Anyways, so let me run this program, and if I'm not wrong, I think this might take a bit of time. So let me run and let's see. Yep, it's starting. It has started to save all the images. It will take a bit of time to save all the images. Right now it's like in 6,000, it will go up to 60,000, and then it will do the test, and there is 10,000 images in test as well. It'll take a few seconds, and let me check the images in the meantime. So you see under under MNIST Dataset, there should be something called a train, and there should be another called a test folder after some time, like because in the program, if you see, it's still the train images that is going on here. So inside the train folder called train, I have one folder for every class, that is from 0 to 9, and inside 0 I have all the images that correspond to 0, and same for 1, and so on. In this way you can save the images. Maybe we'll wait a bit. It should not be. We have done, like, we've gone through half of it already, like at 30,000. There can be a question that why am I saving in this directory structure, especially like why am I having a folder for train and then folders corresponding to every classes? Why not in some other way? The thing is that normally, say when I develop deep learning algorithms, there is a special function within that in the PyTorch API that I use, which allows me to directly load images when they are stored in a folder structure corresponding to this, that is images sorted inside folders respective of their classes. So that function allows me to directly use those images and pass it into our neural networks. And that's why I like this folder structure very much. You can obviously store in different folder structures as per your need or as per the need of the algorithm, but this one works pretty well. And anyways, whenever you're working with algorithms, you will never be working with these image files. You will be always be converting these image files into some numpy array or numpy or any kind of array with the pixel values, and you will be working with those values. Okay, the train folder is almost complete now. Yeah, the test folder is also complete. So we have all the images extracted in two folders, train and test, inside which there are the classes for every image. And now it's like you have everything ready for working with the machine learning algorithms. But one more thing, if you're seeing that this is kind of a tiresome way to deal with arrays or say images. Now if in the future we need to generate this array again, we either have to parse this ubyte files or we have to read from the saved images. So another way is to use something called Pickle. Now Pickle is something that, if you see, with Pickle I can dump or rather save an entire Python object or a Python data structure as a single file. And when I load that file back into the Python environment, what it will do is it will give me that exact same data structure format that I was using during saving the Pickle file. So it goes with very two simple commands. So we have the data path, and we know that the data dict is the dictionary that we want to save. So we open a file called say MNIST data.pkl, which is a Pickle file extension, default Pickle file extension. We open it in a binary mode, and using this file pointer we will call this function called pickle.dump. We'll pass our dictionary or array or list or object or whatever we have, and we will also give the file pointer, and it will create a file with this name in the location that we have provided. And we can load them back with a similar way, but using a command called pickle.load, which will return me the same data structure, and we can store it in another variable as we want. So let me run this for you. So if you see, this is a file called MNIST that we have just created, and we have loaded it back again and saved in something called a new dict. Now if you see, if I print the new dict.keys, it's the same keys that was there. We can also check, like say new dict test images dot shape is still the same shape, like 10,000 cross 28 cross 28, which I showed before. And so this is also a very healthy way of saving large data structures, and because after all it's just a single file, and it's much less hassle. Like if you have to copy it from place to place, it's a much less hassle. You have much less number of inodes in your directories. So saying all that, I really hope that this will give you some insight on how to work with raw data and how to convert your raw data into a data structure which can be used for machine learning algorithms. I will use this data structure, or I will use this MNIST dataset as well for some of my future videos, in which I will be explaining some basic machine learning algorithms, some like classification or some clustering, something like those. And if you want to see those again, subscribe to the channel so that you can get the updates. Also don't forget to click the bell icon for the notifications. And if you like this video, drop a like or just comment. If you have to say something, or if you have any doubt or you want to ask something, feel free to comment below. And with all that, have a very good day. Thank you so much. Bye bye.